All right, we're continuing on with 7.7, the midpoint rule, trapezoidal rule, and Simpson's rule. Okay, problem number 2. Y equals x cubed between 1 and 2 with n equal to 8. So break the interval from 1 to 2 up into 8 pieces. That means delta x is 1/8. So each of these is 1/8, 1 and 1/8, 1 and 2/8, 1 and 3/8, 1 and 4/8, 5/8, 6/8, 7/8, 8/8, and so on. When I punch it in my calculator, it's probably easier to have it in decimal form. So 1.125, 1.25, 1.375, 1.5, 1.625, 1.75, 1.875, and 2. Then I need all the midpoints halfway between these. And how do I find a halfway point? You can average the two numbers. So the average between 1 and 1.125 is 1.0625. The average between 1.125 and 1.25 is 1.1875, and so on. 1.3175, 1.4375, 1.5625, 1.6875, 1.8125, and 1.9375. These are the 8 midpoints. So M8 is delta x, 1/8, and then 1 times all the function values, which means you don't have to do anything to it. So the function values at the midpoints, 1.0625, 1.1875, 1.3175, and so on, up to f of 1.9375. Okay, the function is the cubing function, so I cube all these guys. So it's 1/8, 1.0625 cubed, plus 1.1875 cubed, plus 1.3125 cubed, and so on, up to 1.39375 cubed. Punch it in your machine, it's about 3.744141. Okay. Trapezoidal rule, delta x over 2, 1/8 divided by 2, which comes out to be 1/16. Do not pick the midpoints, just the endpoints. So there are 9 endpoints. Notice 8 midpoints, but 9 endpoints. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So it's 2 times all the in-between guys, but only 1 times the beginning and the end. So 1 f of 1, 1 f of 2, f of 1, f of 2, but 2 times all the in-between ones. 2 times f of 1.125, 2 f of 1.25, and so on, up to 2f of 1.875. So everything from here to here gets a coefficient of 2. The first one and the last one only have a coefficient of 1. All right, so it's going to be 1 times 1 cubed, and then notice 2, 2, 2, 2, 2, 2, 2, and then 1. So 2 for all the in-between endpoints, 1.125 cubed, 1.25 cubed, 1.375 cubed, and so on, all the way up to 1.875 cubed. They all have a coefficient of 2. And then finally, the last one, 1 times 2 cubed. Punch in your calculator, 3.761719. Simpson's rule, delta x over 3. So delta x over 1, which means 1/8. Delta x over 2, delta x over 3. 1/8 divided by 3 is 1/24. And I use the same 9 endpoints, but the coefficients will go 1 here, and if n is even, 4, 2, 4, 2, 4, 2, 4, 1. Okay. So 1 times f of 1, then 4 times f of 1.125, then 2 times f of 1.25. It's the same values as all these, except the coefficients are different. 4, 2, 4, 2, 4, 2. Finally, 4f of 1.875, the second to the last one. And then now that I reached the end, it's 1 times f of 2. Okay, so 1 times 1 cubed plus 4 times 1.125 cubed plus 2 times 1.05 cubed, 1.25 cubed plus 4 times 1.375 cubed, and so on. 2, 4, 2, 4 times 1.875 cubed plus 1 times 2 cubed. Punch it in the machine, 3.75. Okay, so you can see they're fairly close. Okay. What's the actual value? I believe if you actually integrated this, we get 3.75, which indicates that Simpson's rule was the best decimal approximation. Oh yeah, we have it here. Integral from 1 to 2 of x cubed dx, x to the 4th over 4. Plug in 2, you get 16 over 4 minus 1 over 4, 15 over 4, which is 3.75. So you can see Simpson's rule gave us the exact answer, 3.75. Trapezoidal rule, a little bit higher. Midpoint rule, a little bit lower. Okay. All right, number 5, y equals 1 over x between 1 and 4 for n is equal to 6. Okay, so 1 to 4, that's a length of 3. Chop it up into 6 pieces, so delta x is 1/2 or 0.5, right? 4 minus 1 is 3. Chop it up into 6 pieces. So delta x is 0.5, so 1.52, 2.53, 3.54. And here are my 6 midpoints. 1.25 is halfway between 1 and 1.5. And 1.75 is halfway between 1.5 and 2, and so on, and up to 3.75. So M6, which means midpoint rule, 6 subintervals, is delta x 0.5, and then don't multiply by any coefficient, just the function value at the midpoints. That's exactly what you did in Calc 1. So f of 1.25, f of 1.75, f of 2.25, f of 2.75, f of 3.25, f of 3.75. Okay? And I plug into the function, which is the reciprocal function. So it's simply 1 over these guys, 0.5, 1 over 1.25, 1 over 1.75, 1 over 2.25, and so on, up to 1 over 3.75. Add them all up, punch it in the machine, 1.376934. Okay. Trapezoidal rule T6, delta x over 2, 0.5 divided by 2. Do not use the midpoints, use the endpoints, of which there are 1, 2, 3, 4, 5, 6, 7. Okay, so 6 midpoints means 7 endpoints. You use 7 values for both the trapezoidal rule and the Simpson's rule. You don't have to pick the midpoints. So we say, when do I use the midpoints? Midpoint rule. Kind of makes sense. So 0.5 over 2, 1 f of 1, 2 f of 1.5, 2 f of 2, 2, 2, 2 f of 3.5, finally 1 times f of 4. Okay. And the function is the reciprocal function, 1 over x. So if we multiply by 2, it's just going to be 2 over whatever. So notice it's going to be 1 over 1, and then 2 is in the numerators, all the rest, right? 2 over 1.5, 2 over 2, 2 over 2.5, 2 over 3, 2 over 3.5. And then once I reach the end, it's 1 again over 4. Punch in your machine, 1.405357, roughly. Okay, S6, Simpson's rule, delta x over 3, 1/2 divided by 3. Use the same points. This is 1, this is 1, and then it's going to go 4, 2, 4, 2, 4. Second to the last one should be a 4, and then 1. That's always going to work if n is even. So 1/2 divided by 3 is 1/6. 1 for f of 1, 1 for f of 4, and then 4 f of 1.5, 2 times f of 2, 4 times f of 2.5, 2 times f of 3, 4 times f of 3.5, and then 1 times f of 4. So again, that basically means the numerators, the function is 1 over x. So the numerators just become these coefficients. So it's 1, 4, 2, 4, 2, 4, 1. And then I just progress through the mid endpoints. 1, 1.52, 2.53, 3.54. Punch it in the machine, 1.387698. Okay, so making a nice little table here, we have this. All right, and quick note, this is easy to integrate. Integral of 1 over x is ln absolute value of x. Plug in 4 and you plug in 1, but ln of 1 is 0, so the answer should just be natural log of 4. So we'll just get a calculator here quickly for natural log of 4, 1.3862. So Simpson's rule again looks like it's the best. And these two are pretty close also. Okay. So those are some more, and maybe I'll just show you one more, which was interesting, number 3. Y equals 2x plus 1 from 4 to 7. Okay, now, y equals 2x plus 1 is linear which means I can't find the exact value of this thing. If I do a little bit of geometry. In fact, yeah, we can probably spend the time to do that if we wanted to, but that's 3, right? And if I plug in 7, I would get 15. Plug in 4, I get 9. So the average of those is 12. 3 times 12 is 36. So the exact value is 36. Okay, I'm using the formula for the area of a trapezoid. It's average base times height. Okay, this base is 9, 2 times 4 plus 1. This base is 15. What's the average of 9 and 15? 12. 12 times 3 is 36. Okay, so again, chop it up into 6 pieces. Delta x is 1/2. 7 minus 4 divided by 6. So 4, 4.5, 5, 5.5, 6, 6.5, 7. And then the midpoints, right? 4.25, 4.75, 5.25, all the way up to 6.75. All right, midpoint rule. Delta x is 1/2. And don't have to multiply by any coefficient, just the function value at all the midpoints. 4.25, 4.75, 5.25, 5.75, 6.25, 6.75. So you take all of these numbers and plug it into 2x plus 1. So 2 times 4.25 plus 1 comes out to be 9.5. 2 times 4.75 plus 1 comes out to be 10.5, and etc. And 2 times 6.75 plus 1 is 14.5. Add them all up, 36. What does that mean? The midpoint rule gave me the exact answer. We said it was 36. Okay, trapezoidal rule, delta x over 2. So 1/2 divided by 2. Do not use the midpoints. When do I use the midpoint rule? Or when do I use the midpoints? Midpoint rule. So I don't do the midpoints for trapezoidal rule or Simpson's rule. Just use the endpoints. 4, 4.5, 5, 5.5, 6, 6.5, 7. For trapezoidal rule, coefficient is 1, coefficient is 1. That one, that one, that one, that one, that one, all get a coefficient of 2. So 1 times f of 4, 1 times f of 7, but all the in-between guys get a 2. 2 times f of 4.5, 2 times f of 5, 2 times f of 5.5, and so on up to f of 6.5. Okay, and you plug into 2x plus 1. 2 times 4 plus 1 is 9. 2 times 4.9 plus 1 is 10, and then times a 2. And then 2 times 5 plus 1 is 11. 2 times 12, 2 times 13, 2 times 14. That's for 6.5, right? And finally, when you get to 7, coefficient is 1. Grind it all out, 36. Trapezoidal rule gives it to me exactly. And Simpson's rule, delta x over 3. Same 7 endpoints, 1, 1, 4, 2, 4, 2, 4, and then 1. So 1 times f of 4, 1 times f of 7, and then 4 f of 4.5, 2 f of 5, 4 f of 5.5, 2 f of 6, 4 times 6.5, f of 6.5, and then f of 7. So 1 times 9, 4 times 10, 2 times 11, 4 times 12, 2 times 13, 4 times 14, 1 times 15, punch it in the calculator. What do you know? It comes out to be 36, which is exactly what we got over here. And what do we get when we integrate? So by geometry, we got 36, midpoint rule 36, trapezoidal rule 36, Simpson's rule 36. How about if I actually integrate 2x plus 1? Well, x squared plus x from 4 to 7. Plug in 7, 49 plus 7. Plug in 4, 16 plus 4, 56 minus 20, 36. So all 5 methods gave me the same answer, 36. By geometry, by integration, midpoint rule, trapezoidal rule, Simpson's rule, which is what we would expect to happen in this particular case. Okay. All right, so that was it for this section. I'll speak in a little bit of 7.8, which is something called improper integrals. Talk about what improper integrals are, and that's the last section before the test. So test on Friday. 7.8, we have 5 to 33 odd. So improper integrals. Improper integrals, page 527. All right, so we had to go as high as problem 33, I believe it was. Let me show you the homework. And by the way, we say improper integrals, which leads you to believe all the integrals we've been doing so far are proper. It's correct, just like proper fraction, improper fraction. So what makes an improper integral? So while I show you the homework, and let you guess what it is that might make something improper. So page 534 is where we're at. Whoops. Okay, what do we have to do again? 5 to 33 odd. So casually look at 5, 6, 7, 8. Okay, so what do you notice as I'm showing you this? I see infinity, right? I sometimes see negative infinity. And it looks like sometimes I see both of them. All right, so there we go. So it looks like one definition of improper integral is if there's an infinity or negative infinity, or maybe both of them. Right? I think somewhere there was both of them. Yeah, like that one. Then I noticed there's some problems later that don't have infinity or negative infinity. So what's so improper about them? Right? Okay. So what do I do if I have an infinity or maybe a negative infinity? What should I do? Right? Okay. So 7.8, improper integrals. If I integrate from some a to infinity, which basically means you never stop. You keep going as far as you want to the right. So maybe the picture is something like that. Figure 3 on page 528. From a to infinity. So you just keep going forever. Right? So on the one hand, you might say, well, there's going to be an infinite amount of area because you're going forever out. Yeah, but in this case, well, maybe not, because maybe you have a picture like this where you're getting a smaller and smaller and smaller amount. But notice if we stop anywhere, we have a proper integral. Suppose I stop at 10 billion, it's very well defined. Then we say, okay, what happens if I shove it further to the right and further to the right? In other words, I'll evaluate from a to some b, and then take the limit as b approaches infinity. So integral from a to infinity of f of x dx means, suppose I stop at some b, calculate my integral for b, and then take the limit as b approaches infinity of the integral from a to b of f of x dx. So that's what we're going to mean by an integral involving infinity. Integral from a to infinity. Let's just integrate from a to b and take the limit as b approaches infinity, like we did in Calc 1. Okay, so here's an example. Integral from 1 to infinity of 1 over x squared dx. So it's a falling graph, and we say, do I get an infinite amount of area or do I not get an infinite amount of area? Okay, so by definition, I take the limit as b approaches infinity of the integral from 1 to b of 1 over x squared, which is x to the minus 2 dx. Okay, so limit b approaches infinity, power root, x to the minus 1 over minus 1 from 1 to b. Take out the negative, that's 1 over x. So negative the limit as b approaches infinity of 1 over x from 1 to b, which is the opposite of plug in b, you get 1 over b, minus plug in 1, minus 1. Now when b gets really, really big, b becomes 1,000, a million, a billion, a trillion. This thing approaches 0. So I have negative of negative 1 or 1. So the answer is 1. I have a finite amount of area, 1. And the language we say is that if this integral comes out to be a real number, we say that the integral converges or is convergent. If we don't get a real number, then we say the integral diverges or is divergent. Okay, and I'll show you that a little bit later, both examples. Our last chapter, chapter 11, we're going to do a lot more with convergence and divergent situations. But for now, if you get a real number, the integral converges or is convergent.
If you don't get a real number, we say the integral diverges or is divergent. I'll write that for you later, but we don't need to worry about that right now. Okay. Let me show you the integral from 1 to infinity of 1 over x dx. It seems to have the same general shape. Well, let's see what happens. Okay, so limit as b approaches infinity, integral from 1 to b of 1 over x dx. So integral of 1 over x is ln absolute value of x. So limit b approaches infinity of ln absolute value of x from 1 to b. B is a positive number, so I can drop the bars. 1 is a positive number, so I can drop the bars. So limit b approaches infinity of ln b minus ln 1. ln 1 is 0. But now when b gets big, ln b gets big, right? The natural log function looks like that, sort of. So when x gets big, y gets big. So the answer is infinity. So this is an example of an integral which diverges or is divergent. Okay. So here you get an infinite amount of area under the curve, believe it or not. Here you don't. So underneath 1 over x squared, you have a bounded area, 1. Change it to 1 over x, all of a sudden you get an infinite amount of area. Okay, so that's what we have. All right, and next time I'll get started with some of the problems on 7.8 on improper integrals. But for now, I think I've done 4 out of the 6 in 7.7, so we're done with that. And next time we'll do 7.8.